Hey everyone, Dr. Kem here, and welcome to today's Explainer. Have you ever wondered how we can find a single solitary toxic molecule hidden inside an entire Olympic-sized swimming pool? Well, today we are unlocking the absolute powerhouse that makes that possible, Atomic Absorption Spectroscopy, or AAS. Whether we're hunting for trace metals in our drinking water, screening biological fluids in a clinic, or investigating a forensic crime scene, AAS is literally a foundational pillar of modern analytical chemistry. We're going to explore this technique completely, starting all the way down at its quantum mechanical roots, right up to the cutting-edge calibration strategies used in the world's top labs.
Okay, let's take a really quick look at our roadmap for today. We'll be hitting 1. History and principles, 2. Inside the spectrometer, 3. Interferences and correction, 4. Comparing FAAS and GFAAS, 5. Applications, pros and cons, and finally, 6. Safety, advances, and a summary. We've got a lot of ground to cover, so let's jump right in.
Section 1. History and core principles. We're kicking things off by looking back at the brilliant pioneers who first noticed how light and atoms interact. It's actually kind of wild to think that the fundamental physics of AAS were observed over a century before anyone figured out how to use them in a lab. Back in 1802, Wollaston spotted these mysterious dark lines in the solar spectrum, which Fraunhofer later spent ages meticulously mapping. But it was Kirchhoff and Bunsen who really connected the dots, proving those dark lines were caused by cooler atoms absorbing very specific wavelengths of light. Fast forward a few decades, and Niels Bohr totally revolutionizes atomic theory with quantum mechanics, proving atoms only absorb energy in discrete, quantized amounts. But you know, it wasn't until 1955 that Sir Alan Walsh had the ultimate light bulb moment. He realized we could use this exact quantum principle to precisely measure trace metals in a commercial laboratory. So the absolute mathematical backbone of this entire technique is the Beer-Lambert Law. Absorbance equals epsilon LC. Because we're dealing with quantum mechanics here, ground state atoms only absorb very specific, incredibly narrow bandwidth photons. This means if we shine the exact right wavelength of light through a cloud of free atoms, the amount of light that disappears is strictly mathematically linear to how many atoms are hanging out in that cloud. But let's be real, the physical universe is always a bit messy. Things like Doppler broadening, which is just from the rapid, chaotic movement of atoms, and collisional line broadening naturally widen these absorption profiles. And that is exactly why we desperately need incredibly narrow light sources. Without them, our elegant mathematical relationship bends, our calibration curve flattens right out, and we totally lose our ability to accurately calculate concentration. Moving on to Section 2, Inside the Spectrometer. Let's see how a physical sample actually gets transformed and measured inside the hardware. The journey our sample takes is practically a masterclass in physical chemistry all on its own. After some really rigorous sample prep, like acid digestion to tear down complex matrices, the liquid has to be nebulized, desolvated, and ultimately vaporized into the free, ground-state gaseous atoms we actually need to absorb the light. Standard flame AAS handles this by just aspirating liquid directly into a roaring fire. But for the tricky elements, we have to get creative. For instance, cold vapor AAS, or CVAAS, is this highly specialized technique used almost uniquely to detect mercury at room temperature. And then there's hydride generation AAS, or HGAAS. This is an absolute lifesaver for chemically isolating highly volatile elements like arsenic and lead from really messy biological matrices before they even get near our optical path. Bridging the gap between the theory and what you actually run in the lab. Let's talk about the electrothermal atomizer, which pretty much everyone just calls the graphite furnace, or GFAAS. Unlike that continuous roaring flame we just mentioned, here we're dealing with a microscopic sample. We're talking maybe 5 to 50 microliters. It gets injected directly into this tiny pyrolytically coated graphite tube. We then pass a massive electrical current directly through the body of the tube itself, heating it up with just incredible precision to atomize the sample. When you're using electrothermal atomization, your tiny sample goes through a literal trial by fire. It's a highly controlled, intense three-step process. First up, drying. We bring it just above 110 degrees Celsius to gently evaporate the solvent without aggressively boiling it. Next, we crank the heat up to around 1,000 degrees for the ashing phase. This physically burns away all that complex, gunky organic matrix. Finally, the main event, atomization. We blast the furnace with hundreds of amps of electricity. Temperatures instantly soar to over 2,000 degrees Celsius, creating this incredibly dense, localized cloud of free atoms suspended right in our optical path, but just for a few fleeting seconds. Now think of your light source as a highly specific lock and key. Usually, we're using a hollow cathode lamp, or HCl. It emits narrow radiation that can only be unlocked and absorbed by ground-state atoms of that exact same element. Pretty clever, right? But for some of those volatile elements like arsenic or selenium, we often have to upgrade to electrodeless discharge lamps, or EDLs. They just give us way greater light intensity and a nice boost in sensitivity. So this highly specific light passes right through our atomic cloud, enters a monochromator to isolate the precise analytical line we care about, and finally strikes the detector to spit out our reading. Section 3. Interferences and error correction. Look, even the most elegant analytical setups hit roadblocks. Let's talk about what messes up our data and how we fix it. Interferences are the absolute enemy of accuracy. First, we have spectral interference. This is when background molecules or smoke just eat up our light. How do we fix it? Clever background corrections. We might use a deuterium arc lamp, the D2 correction, to measure and subtract the broad background. Or we use Smith-Heaftsche self-reversal. Or, my personal favorite, the highly advanced Zeeman effect, which uses a powerful alternating magnetic field to literally split the atomic lines and isolate the true target signal. Then we have chemical interferences. This is when elements decide to bind together, like calcium stubbornly forming refractory compounds with phosphate. We blast through this by using higher temperature nitrous oxide flames, or by tossing in a chemical release agent like lanthanum to free up our target atoms. Finally, physical interferences. This is usually caused by thick, highly viscous samples. To beat this, we have to use strict matrix matching, or the method of standard additions, so our calibration actually holds true. Section 4. Comparing FAAS and GFAAS, flame versus graphite furnace. These are the heavyweights, but they have totally different day jobs. So when you're deciding on a method, you really have to weigh your options. Flame FAAS gives us incredibly stable precision, a relative standard deviation of under 1% for parts per million levels. Think of FAAS as finding one specific drop of water in a standard bucket. It's fast, it's continuous, it's a workhorse. GFAAS, on the other hand, it operates at sub-parts per trillion sensitivity. That is literally finding one specific drop of water inside an entire Olympic swimming pool. The catch is, it takes minutes per sample, but it's hundreds to thousands of times more sensitive. We actually quantify this mathematically. We use characteristic concentration for flame and characteristic mass for furnace, which tells us the exact amount of analyte needed to produce a standardized 0.0044 absorbance signal. Section 5. Applications, pros and cons. Where does all this chemistry actually meet the real world, and what are the trade-offs? Honestly, AAS is essentially the invisible shield protecting our daily lives. Environmental agencies rely on it to hunt down heavy metal runoff in local rivers and soils. The pharmaceutical industry absolutely depends on it to prove that toxic metal catalysts haven't leached into life-saving medications. It's also everywhere in clinical settings for testing blood and urine, out in agriculture verifying the safety of our food supply, and in forensic labs where figuring out the exact elemental profile of a tiny soil sample can literally place a suspect right at the scene of a crime. While it's a fantastic tool with awesome sensitivity and surprisingly accessible operating costs, we have to be real about the limitations. Sure, you can analyze about 70 different elements, but traditional AAS forces you to physically swap out a specific hollow cathode lamp for every single one. It makes it a pretty slow, sequential, one element at a time process. Plus, the linear dynamic range is fairly moderate, especially when you compare it to a beast like ICP-MS. Because the Beer-Lambert Law doesn't stay perfectly linear at higher concentrations, thanks to self-absorption and line broadening, if your samples vary wildly in concentration, you're going to have to pause, do a bunch of manual dilutions, and run the whole sequence all over again. Section 6. Safety, Advances, and Summary. Let's bring it all home with lab safety, some amazing new tech, and our final takeaways. We have to talk safety. Never, ever underestimate the physical hazards here. We're dealing with incredibly volatile aeracetylene flames and intense UV radiation from the lamps. But beyond keeping your eyebrows intact, there's your analytical safety, your quality control. A true master analyst never just blindly trusts a single instrument reading. They heavily rely on certified reference materials, or CRMs, to anchor their accuracy. They're always running routine spike recoveries to check for hidden matrix effects, running procedural blanks to monitor for contamination, and doing daily instrument tuning to guarantee their data is absolutely bulletproof. Okay, this is where it gets really exciting. Representing the single biggest leap since Walsh's original work in the 50s, we have high-resolution continuum source AAS, or HRCS-AAS. This completely revolutionizes the field. By using a super high-intensity xenon short-arc lamp paired with a double-eshel monochromator, which basically acts as an ultra-precise optical sieve, and a modern CCD array detector, we can suddenly scan wide spectral windows all at once. This completely neutralizes that annoying single-element limitation of traditional AAS. It brings the technique firmly into the era of true multi-element, high-throughput analysis, and, get this, It even allows for molecular speciation.
All right, let's lock this in. Here is your core masterclass sequence for this incredible technique. It all starts with rigorous sample prep and digestion. Next up is precise atomization, whether by flame, furnace, or chemical vapor. That's followed by highly selective photon absorption, all strictly governed by the Beer-Lambert Law. And finally, meticulous mathematical data correction using powerful tools like Zeeman or deuterium background correction to strip away any interferences and reveal the truth of your sample.
So I'll leave you with this provocative thought. With the sheer analytical power to detect down to the parts per trillion level, what hidden elements do you think are currently lingering in the water you drink, the food you eat, or the blood running through your veins right now? I'm Dr. Kem, and thank you so much for joining this deep dive explainer on atomic absorption spectroscopy. We've gone from the quantum leaps of electrons all the way to the practical realities of keeping our modern world safe and rigorously tested. Keep asking questions, always verify your blanks, and I will see you in the next explainer.